In this second part of utility cuts in paved roads, we'll continue looking at ways for local government agencies to improve utility cut work methods and management, beginning with pavement cutting. First, it's important to re-emphasize safe work zones. All traffic control devices, flaggers, and the work zone as a whole should be checked often for compliance with the minimum requirements of the MUTCD and with all state and local regulations. When cutting pavements, care should always be taken to make neat, straight, vertical-sided cuts, but especially when the sides of the cut will end up as the edges of a permanent patch. Many agencies instead make temporary patches initially and later replace them with permanent ones. In any case, utility cuts must be laid out properly, in the correct location as previously marked, and to the proper dimensions. These proper dimensions must allow room for the utility facilities, workers and equipment, and the operations that will take place, including compaction of backfill. At least 460 millimeters of space should be allowed on each side of a facility. Of course, other factors may indicate that a wider cut is required, such as to accommodate a trench box or other type of shoring or bracing. In cutting asphalt pavements, the perimeter line should first be marked. White is the recommended marking color, so as not to be confused with any other utility markings in the area. Then a saw cut should be made along the lines, either full depth or partial depth. When partial depth, the sawing should cut to 1/3 the depth of the pavement, or at least 50 millimeters. Then a mechanical hammer should be used to cut the rest of the way down. The hammer should have a cutting edge of at least 100 millimeters. Alternatively, asphalt pavements may be cut with the mechanical hammer alone. However, in this case, the cuts should be squared before final repairs are made. The edges of all cuts should be vertical and straight. Hammer operators should be safely attired. Hard hat, safety goggles, ear protection, and sturdy steel-toed boots equipped with foot guards. When cutting concrete pavements, the outline of the cut should be sawed at least 200 millimeters beyond the edge of the trench, at a depth of no more than 38 to 50 millimeters regardless of slab thickness. This saw cut will provide a straight, vertical face that will not spall. It's a good idea to make additional, less deep saw cuts parallel to the outline cut and a few millimeters away from it. These cuts provide a toe hold for the hammer's breaker point and help to remove the concrete without spalling the adjacent pavement. Then a worker can begin breaking out the concrete below the saw cut with a mechanical hammer. This produces a rough face to place the concrete against when it's time to patch the cut. The existing pavement and new patch will tie together through aggregate interlock. Whatever the type of pavement, backhoe front end loaders are typically used to further break out the pavement and remove the debris from the trench area. Other types of equipment may also be used. Once the pavement has been cut through and the pieces are removed, the next step is excavation. A number of issues must be looked at here, all of them having some relationship to safety. First, it cannot be stressed too much. Locate all underground utilities in the area before starting to dig. In highly congested areas, consideration should be given to using non-destructive vacuum technologies to locate, uncover, and repair existing facilities. A little extra work up front can save time and money. Then, during excavation, crews must avoid contact with all utilities, above or below ground. In particular, backhoe operators should never dig too close to the facilities they're uncovering. Instead, hand tools should be used when in close proximity. Crews should always be alert for unanticipated facilities too. Attention must also be paid to any surface encumbrances next to the trench. This means structures, trees, signs, or whatever else that might get in the way or fall in, such as this curb and gutter section. They should be identified and then moved or supported. All warning systems should be checked for proper placement and functioning. Advanced signs, barricades and other devices around trenches, backup alarms for heavy equipment. Not only workers and motorists need to be warned, but also pedestrians. Cave-ins are often a concern with utility trenches. Excavations deeper than 1.2 meters must always be shored or braced. Loose soils may require shoring at lesser excavation depths. Typically, trench boxes are used in utility cuts. Spoil banks and equipment should be kept at least 6/10 of a meter away from trenches to keep them from falling in. Proper access and egress for both workers and equipment is another issue. Trenches deeper than 1.2 meters must have exits, ladders, stairways, or ramps, placed so that workers don't have to go more than 7.5 meters to reach one. Any danger to the workers from falling loads should be avoided. Workers should be kept away from loads during digging, and operators should be protected too. Of course, hard hats are a must for everyone on the job. Hazardous atmospheres is a term that refers to unsafe air in trenches. Dust and smoke are harmful enough, but toxic, flammable, or asphyxiating gases can be deadly. A calibrated, direct reading instrument should be used to indicate when there's not enough oxygen in the trench, or when a volatile or toxic gas is present. When unsafe air is likely, emergency breathing equipment should be close at hand. A warning, however, using such equipment requires properly trained personnel. Other emergency rescue equipment should be nearby too, according to OSHA regulations and agency or company policies. Other trenching issues include proximity to traffic, wet excavation, stability of adjacent structures, loose soil, fall protection, and finally, daily inspections to check all conditions. Not all of these issues arise with every utility cut, but as they do, each one should be considered and the necessary steps should be taken. New technologies and advances in existing ones promise to improve trenching operations or, in many cases, replace them altogether. For example, jacking and boring are trenchless methods of installing pipes beneath roadways. They have been in use for some time, but continue to be improved. Live insertion, small hole vacuum excavation technology, service terminations utilizing specially designed extension tools, pipe lining, and pipe bursting are newer procedures for rehabilitating or replacing existing pipes. Such technologies should be considered as alternatives to conventional trenching when costs and other factors permit. Of course, the object of utility cuts, or of trenchless methods, is to install new utility facilities or repair or modify existing ones. That work, naturally, is the specialty of the utility company or contractor, and it's not our purpose to discuss it here. But once the installation, repair, modification, or whatever is done, inspected, and approved, it's time to cover it up and proceed to backfill the trench. Backfilling normally suggests putting back the material that was dug out of the trench, and generally that's the case. The fill material should match the subgrade of the rest of the roadway, if suitable. But sometimes certain subgrade materials are okay only as long as they're left undisturbed. Once excavated, their properties make them unsuitable for reuse as backfill. After all, there's quite an assortment of materials down there underlying our roads and streets, especially in older urban areas. Besides a variety of soils and natural and crushed stone and gravel, there may be large rocks, muck, cobblestones, bricks, railroad ties, and all sorts of debris. Such materials must not be included in the backfill, but must instead be discarded. Usable backfill includes granular materials, clay, sand stabilized with cement, and non-shrink fill. Here, for example, a water company has begun backfilling this trench with gravel that serves as bedding for the pipe. Then the soil excavated from the trench is put back and compacted in loose layers about 150 millimeters thick. Finally, when the backfill reaches about 3/4 of a meter from the top of the trench, a specific class of crushed stone is placed and compacted in layers. Then, on top of this material, a temporary patch will be constructed. Non-shrink fill, also called unshrinkable fill and flowable fill, is an alternative to soil backfill. It's a concrete-like mixture, minus the coarse aggregate, and with enough water to make it flow readily. The advantages of non-shrink fill are that it allows for narrower trenches, is placed easily and quickly, easily flows into and fills up hard-to-reach areas, displaces any standing water, self-consolidates, attains maximum density, doesn't settle, can be dug up, and requires less inspection. Disadvantages include its non-availability at times and in some locations, and the need to protect it during the setup period. Steel plates are probably the best means of protection during setup. Although non-shrink fill may be increasing in use, traditional soil backfill still predominates. And that means that compaction is still a key issue. A variety of equipment is used to consolidate backfill layers. Most often, manually operated gas-powered or pneumatic-powered tampers. But larger, self-propelled equipment may be used where trench size permits. Regardless of the equipment, the backfill should always be placed in layers or lifts, about 150 millimeters in loose depth. Each lift separately placed and compacted right on up to the top of the subgrade. The goal is to build a dense mass of fill that will not later settle under its own weight or from pavement or traffic loads. Typically, agencies specify that utility cut backfill be compacted to 95% of maximum density, as determined by standard Proctor tests. The only way of knowing for sure that such a requirement has been met is through density testing. By such methods as nuclear gauge, sand cone, or Clegg impact tester. In terms of how they test the actual density, how frequently they test it, or indeed whether they test it or not, agencies vary. More of them should consider density testing. Otherwise, they need to rely on stricter requirements for lift thickness, compaction equipment, and number of passes. Once utility cuts are completely and properly backfilled, the next step in the process is surface restoration. Here and there, utility cuts may be made in streets paved with brick or cobblestone, but most utility cuts are made in pavements of concrete, asphalt, or asphalt over concrete base. The pavements disrupted by utility cuts should generally be replaced with similar materials. But another variable is whether the repair will be permanent or temporary. Many agencies make temporary pavement patches when utility cuts are closed and then later return to permanently patch these locations, for example, during the following spring. Although temporary patches will eventually be replaced, they must still be constructed well enough to not settle or disintegrate during the short run. Cold bituminous mix is typically used for temporary patching, whether in asphalt or concrete pavements. Placing the right amount of mix in separate layers and compacting each layer properly are key steps in making a good temporary patch. Enough mix should be placed and compacted to leave the patch slightly above the level of the surrounding pavement. Traffic will further compact it. Of course, if too much mix is placed, the patch will become a bump. And if too little is placed, traffic compaction will form a depression in the road. In making a permanent asphalt patch, the perimeter of the repair area should first be marked, beyond the limits of the temporary patch. The perimeter should be rectangular, with straight sides, even though the temporary patch may have been irregular in shape. The sides should be either parallel or at right angles to the roadway center line. Then the pavement should be saw-cut, both to facilitate removal of the pavement inside the patch perimeter and to help produce straight vertical sides. The patch area should then be broken out. The debris should be removed, and the side should be clean, vertical, and straight. Now, when the pavement consists of asphalt over a concrete base, the next step is to moisten the subgrade and sides of the patch, and then place concrete. But even when the pavement is full-depth asphalt, many agencies require a concrete base for their patches. Here, for example, a 200 millimeter thick concrete base is being constructed. Because the permanent patch is larger than the temporary one, and therefore larger than the dimensions of the trench, the concrete base spans the trench area. The rigid slab won't settle even if the trench backfill does. When the lane or lanes must be reopened to traffic, the patch may be protected with a steel plate to allow the concrete to set up and completely cure. Once it's cured, the concrete should be covered with hot mix to form an asphalt cap. The asphalt should have a uniform thickness of at least 50 millimeters. When a full-depth asphalt patch is constructed, without a concrete base, it should be at least as thick as the original pavement, or at least 100 millimeters in any case. Also, the mix should be placed and compacted in separate, uniform lifts. Mix temperature requirements should be complied with whether the asphalt patch is full depth or cap only. Proper compaction procedures should likewise be observed in either case. The patch edges should be compacted first. Then the entire patch should be rolled in both directions. The finished patch surface should be smooth and conform to the surrounding pavement surface. No bump, dip, or other noticeable difference in the riding quality. Concrete patches for utility cuts should be made by following the same established procedures used in constructing all concrete patches. With the pavement surface satisfactorily restored, the final task is site cleanup. All work materials and equipment must be removed from the job, and the pavement and adjacent areas should be thoroughly cleaned up. A combination of power equipment and manual work is typically required. Remember, every work site is in someone's neighborhood. A good cleanup job not only makes the area look better, but also makes it safer. Finally, traffic control signs and other devices should be removed in reverse order to the way they were set up. When work will continue into the next day, open trenches must be safely barricaded to keep vehicles and pedestrians out, or covered with steel plates. Traffic control devices that don't apply after hours should be removed or covered. As long as utility facilities are located beneath our roads and streets, government agencies, utility companies, and contractors must do everything possible to ensure that utility cuts are made and repaired correctly and safely, with minimal disruption to traffic, and without leaving behind a defective pavement.